So this is the other analysis that we do here. And that's maybe a little more interesting because here we are really looking into the anatomy of the damage in our patients. So we are here. Now we want to statistically compare images. We want to compare the image of our patient with the image of a series of healthy controls. How does it work? So essentially here we are running a two-sample t-test. So just the standard test that you use to compare groups. Here we are comparing one patient with a group, but the underlying design is the same. So we really want to see and see if the value of metabolism in each voxel in the brain of our patient is significantly, so there is a statistical comparison, significantly different compared to the mean value that we can observe in our second group, which would be the healthy controls, of course. And we do this because we want to obtain these kind of maps with the statistical deviations in the brain metabolism of our patients at voxel level. So we are working with massive univariate analysis. We are doing this for each voxel in the brain of the patient. We compare it to the mean of the healthy controls and derive a t-value. So these are maps that contain t-values. The statistics, these are statistics, and represent the decrease or relative preservation in metabolism of our patient. Very, very quickly, SPM works based on general linear model. So the idea is that we want to, we are doing a two-sample test, but this can be seen as a general linear model. So we have our images, and the idea is we want to see if our condition, our regressors, in our case, is just belonging to group 1, which actually is our patient, or group 2, which is our healthy controls, predicts our the distribution of FDG that we observe. Of course, we have to estimate some parameters in our linear model. This is done by SPM, of course. But the thing is that in SPM, you will see a design matrix that looks like this, because this is simply representing the matrix of regressors that we are using. If you are doing a two-sample t-test, we will have a design matrix like this, representing our group 1, the patient in white, and our group 2 that are the healthy controls. And it just means we are doing a two-sample t-test in the end. Coming to healthy controls, just a note of caution. So I sent you the link to download the healthy controls that we use here. It's 33 healthy controls that have been acquired on our scanner, which is a Gemini TF PET-CT scanner, big bore. The thing is, this scanner has a specific resolution, not the best one. If you have newer scanners, you probably have a better resolution. This is a PET-CT scanner, it's not a PET-MRI scanner. So, if you're going to use these healthy controls with your patients, just be aware that there might be some differences, systematic differences introduced by the fact that we are using different scanners. So it is true that these patients have very, very huge deformations in the brain and huge decreases in metabolism, but just be careful. Ideally, you would want to acquire your own group of healthy controls for all your statistical analysis you might ever do, whether it is disorders of consciousness, dementia, epilepsy, whatever. And just to give you some resources, here are a list of, it's not comprehensive, it's a list and some examples from databases that can be accessed. Some more easily, some more with more complicated detailed applications. These databases include FDG-PET scanners of healthy controls. This number refers to the whole database, so it's not that you have 4,000 healthy controls with FDG, but you can go look into these databases looking for scanners that are as much as similar as what you have. In case you don't have the possibility to acquire your own healthy controls, which should be the gold standard. So try to acquire healthy controls on your scanner. But anyway, so let's assume that you have your healthy controls or you're using our healthy controls, whatever. To run the statistical analysis, I just want to tell you very quickly a couple of things. So first of all, you need to tell SPM to define where to do the statistical analysis. So we just want to compare metabolism within the gray matter. So typically what we tell SPM is that he has to take these explicit masks, which really just defines the brain. So we give SPM an explicit mask, and then we ask SPM to compute a relative mask, which is computed based on the intensity. So we just tell SPM, just take only the voxels that are above a certain threshold. And here it is explained how it is done. And usually this allows us to get a good approximation of the gray matter that is specific for this patient. So it's not just a standard mask, it's a mask computed for the patient. And you will hear more about this, especially from GIGA later. Next, very important. So when we do SPM analysis, we don't use SUV, standardized uptake value, that is used just for the global part. We use something that is can be considered as a standardized uptake value ratio. What does it mean? That we take our intensity, or the activity intensity, and we divide our brain, the signal across the whole brain for the value contained in a reference region. The reference region is just ideally is a region that is spared of the disease, devoid of specific tracer uptake. It's really a region that should allow us to compute this value that should be as much as comparable as possible through different subjects. So we use this reference region. The problem is that one, let's say, requirements on the reference region is that it must be spared by the disease of interest. And with patients with disorders of consciousness, damage can be everywhere. So we cannot use this approach as it is. So something that it is done, it is actually quite commonly done also in other disorders where we are not sure where damage will occur, is to scale our images to the global mean. So we just get the global mean from the whole brain in radioactivity intensity, and we divide the signal in the brain by this value. In this way, you obtain again a value that is scaled. It is comparable across different subjects. And this is what we do. There are other solutions. This is the simplest one that I would like to show you today. There is also other more complicated way to do quantification. This is, of course, an approximation. Then what we have, so since we're using global mean scaling, which by the way is the default in SPM, we have an image that is scaled to the global mean. So we have a relative measurement. It's not an absolute measurement of metabolism. So just be careful, because this affects the interpretation of the maps. So this is a relative measure. It's not absolute. So you will see that we will talk about relative hypometabolism and relative preservation. For that patient. So it really means hypometabolism means these are the regions that are most impaired in that patient's. Relative preservations, these are the regions that are less impaired, more preserved in the patient. It doesn't mean that in absolute terms, these regions have decreased metabolism, but it's just really to get an idea for that patient what is most preserved and less preserved. And this is what we can say when we use global mean scaling. Other thing that we need to set is the contrast, and the contrast basically allow us to ask specific questions to SPM. So we ask SPM to show us, based on the general linear model, to show us only the regions that, for example, show relatively decreased metabolism or hypometabolism. So we set the contrast as -1 + 1, which really means tell me in which voxels the patient, which is here, has significantly less metabolism compared to the control. So -1 + 1, what the patient does not have, that the healthy controls have. So we need to set the contrast. We need to set a statistical threshold. I will be quick here because I'm sorry, I'm running out of time. But the thing is, we need to set a statistical threshold. And here a disclaimer: in group level analysis, when we are comparing a group with another group, it is highly recommended to use thresholds that are corrected for multiple comparisons to decrease the risk of false positives. So for example, you can choose to use FWUs FWE, so false family-wise error correction. This is very common, but it is a very stringent threshold. So and these thresholds have been conceived for really a comparison between groups. Here we're doing something different. We want to compute a map of hypometabolism at the single subject level. If you use this threshold, you will really lose a lot of meaningful information. So you will really miss a lot of hypometabolic regions. So we have a lot of false negative. So what we see that really works for this specific purpose, which is a clinical purpose, is to set a threshold to uncorrected 0.05 and that's it. So we don't even set, we can also set a threshold, which is a spatial threshold. So you can tell SPM, show me only the clusters that survive p-value of 0.01 or whatever, and that have an extent of 100 voxels. So only if we have 100 contiguous boxes that are all below the statistical threshold, show it to me. Here we have so huge alterations that we don't need really to set them, because you will see we get very huge clusters of hypometabolism. So this is the threshold that we use. This is what we obtain. So these are the areas where we have significant hypometabolism. And you can see here a series of statistics in terms of p-values, at the voxel level, of peaks of hypometabolism with their coordinates, and I will show you directly on SPM how to navigate. Any questions? Apparently, no. Okay, so yes. Sorry, you're seeing something you should not see. So first, okay, screen one, perfect. So any questions? I heard some noise. No. Okay, so now we go back to our patient. So patient, where it is here, patient one, which I had normalized and smoothed in the previous hands-on session. And after I show you how to do it, then you will have to do it again in the breakout room. So try to follow. You don't need to do it now. So again, we type SPM-PET in case you closed SPM. Good. We click again on batch, and we load our batch. The batch you have to use now is the SAT batch that is available also on Indico here in this, under this this session, of course. Okay, so I assume you have downloaded the SAT batch. You put it on your computer. I will load it. So here I click on this sign as you did before. So we look for the batch, which I put here. I select with just one click. Done. Now here's a bit more complicated. We have to change a few more things, but just really the first time you do it. After you have set the batch and adapted it to your computer, you will just need to change really the directory and the scan and the scan of the patient. But now you have to do a few more things. So first of all, the directory. We have to tell again SPM where to save our results. And I want to save them into the folder of the patient, of course. So I click on the folder and select the folder with the one dot, and here we are. I selected the correct folder. Then I have to select the scan of my patient. And again, it is very important, here it is, because I'm already in the right directory. It is very important to select the smoothed normalized image. If you make a mistake and select the non-normalized image like this one, you will get an error from SPM, because here we are comparing smoothed normalized image of the patient to the smoothed normalized image of the healthy controls. So that are smoothed and normalized also against the template. So we really have to have images in the same space. If you take this image simply would not be in the same space. We have the wrong dimensions, SPM will get crazy. So select smoothed normalized SWS images. Done. And this is our patient. Group 2, we select our healthy controls, which I already did before. And you can see here you have these healthy controls on your computer because you downloaded it from eBrains. So inside the eBrains folder, you have data, healthy control images, and you just select the patients. So you would do specify. I will not do it. Yeah, I already selected them. If you just click on one image, select all, and you have here 33 images of the healthy controls selected, done. So you have to have 33 here. You don't touch the rest. The only thing left to adjust, just the first time you do this, is the mask. So we need to tell SPM, where is the brain? So we select a mask, which is just a standard brain mask available in SPM. That contains, that's just to tell SPM where is the brain. So we just select the mask, and the mask, again, you can find it. This is inside the coffee break script in the mask templates folder. So you really have everything either here in the mask templates folder or in the data, eBrain's data folders. That's where everywhere you have to be. So we select the mask, brain mask, and that's it. And then we already set a relative threshold to try to get a bit more to the gray matter within this general brain mask. And the rest is just to set the global mean scaling, which is what we are using. And here you don't touch anything. Always remember to save your batch so that at least healthy controls and masks are already selected in the correct way, and you don't have to do it every time. So save the mask, okay, and we can run. Here is the design matrix. Again, we are comparing our patient with a group of healthy controls. Now SPM is estimating things, and it is done already. Great. So it's already done. Now we have some new files that have popped up in our folder. Jitka will tell you later what to do with these files, especially with the mask nifty file. For now, for the results, we just need to go and use this SPM map file. So what we do with this SPM map file, this file simply contains all the information concerning the statistical comparison. We use it now to visualize our maps. So what we do is we click on results. We select the SPM mat, sorry, that has just been computed by SPM, done. And now we have to define our contrast. So we click on T contrast, because now we are doing a two-sample t-test. We are just comparing two things, one patient to a group. And we click on define new contrast. So in this case, we want to look at hypometabolism. So we just give it a name. And then we give a vector of numbers. That's just our way to communicate to SPM what we want to see. And we say -1 + 1. So we want to see what the patient doesn't have that the controls have. We want to see the decreases in metabolism. And okay. Now the contrast is selected. You can also define new contrasts, like and you will see it in the step-by-step tutorial that you have on Indico. But for now, we just stick to hypo. Done. We don't want to apply any masking. We want to use an uncorrected threshold p-value, because that's what we saw works better in this kind of patients. We want to select 0.05. Again, this is what based on practice works, based on experience. We don't set any spatial extent threshold. And here we have our map. So this is, and you can, if you click here, you can see where the peaks of hypometabolism are localized around the brain. And that's it. From this map, you can also try to do some nice renders. So for example, what we use here, what you do is that you click on overlays, render. We have to select the render file that is in the SPM folder, but that you can also find inside our script. So if you go here, you have render SPM 26. This is what we use for the render. This is inside, again, the script mass template healthy controls folder. We select this render. We like to have the old style. And here we have our render. You can change color if you like, because this is hypometabolism. We prefer to indicate it in blue. That intuitively is related to, okay, decreases. So SPM figures, colors, color map, gray, cool. And you can change the color of the map. And that's it. So this is all we do. I will let you try it out.